A patch antenna is a wider chunk of microstrip, like a large rectangle of conductive material, still above a dielectric and a ground plane. So this might be my dielectric, and it might be backed by a ground plane. In general, the height of the substrate is much less than a wavelength. That's true for microstrip transmission line too. And the length of the antenna is going to be approximately half a wavelength in the material. And we usually use lambda G for that, for where G stands for guided. And the guided wavelength is the wavelength in air divided by the square root of the effective dielectric constant. In reality, the length that you need is going to be slightly less than half the guided wavelength because of fringing at the edges, which effectively increases the length of the antenna. And we'll talk a little bit more about that later. And the last dimension of the patch that we have to talk about is its width. So if we talk about its width here, that controls the input impedance. And here's how it controls it. This antenna, the way that we've drawn it, can support this, its fundamental resonant mode in two different directions. You could have current that's flowing predominantly left to right, or you can have current that's flowing predominantly top to bottom. The longer dimension will have resonance occur at a lower frequency because lambda G over 2 approximately equal to L occurs at a lower frequency for the longer dimension. The current distribution on this antenna, if I were to take a slice right through the middle, I'm going to do that in red. Here's a slice. If I take a slice right through the middle and draw a cross section like that, the current distribution on this antenna here's 0, here's L. I'm going to make this dimension X, and this dimension, the magnitude of, I guess I'm going to make that J, magnitude of J. The current distribution is going to go to 0 at either end and have a peak in the middle. The voltage on this antenna is going to do the opposite thing. So over the same region, the voltage is going to have a minimum at the middle and be maximum at one end and minimum at the other end, and have opposite polarity, like that. What this means is the location you put the feed point on the antenna sets the current voltage relationship. If I choose the very center of the antenna, then I'm at a voltage minimum and I'm at a current maximum. If I move it over a little bit, the current voltage relationship is a little different. If I can go all the way to the edge where we're very nearly an open circuit and the current is at a minimum but the voltage is at a maximum. So I have a lot of flexibility here in choosing my feed point to match this antenna. So this is an input impedance tuning thing. I can also tune the input impedance of this by changing its width for two reasons. First of all, because this patch antenna is just a really wide piece of microstrip line, and if you change the width of microstrip line, you change the characteristic impedance, but also because radiation primarily happens from the edges of the antenna, from here and here. And I'm going to talk about that a little bit more now. But since radiation comes from the fringing fields that are leaking out from the edges of the antenna, if you change the area over which that happens, then you change the radiation resistance of the antenna, and you'll change the input impedance too. So here's what actually happens. The way that this antenna radiates is a little weird because we have a horizontal current, right? I said that we have this current that's on the surface of the patch antenna, and it's closely spaced to a ground plane because I said that that spacing, h, is much less than a wavelength. We know from image theory that this is going to create image currents in an opposite direction that will tend to cancel this out, and it'll tend to reduce the radiation resistance of this thing. So it's not going to be a very good radiator, and this current really kind of won't radiate because it cancels itself out. But we can model the radiation coming from this antenna as an effect of the fringing fields on either side, because I said that there was going to be fringing. So it's going to look like this. You're going to have an electric field that points sort of up from the ground plane to the edge of the antenna on one side and down from the edge of the antenna onto the ground plane on the other side. You assume that they're basically flat, and you use the surface equivalence principle to, instead of worrying about what the value of the electric field is, we're going to replace this with a continuous conductor that has an equivalent magnetic surface current on it. I told you that magnetic surface currents would be used sometimes to simplify antenna problems. This is one of the biggest ones where this happens. So as a top view, what we have instead of this situation now becomes we get to remove the antenna, and then we just have these two magnetic currents on the ground plane, where the magnetic current is the surface normal vector crossed with the electric field. But it's still above a ground plane. And we can make this problem one step easier by using image theory to remove the ground plane. And then the radiation from this antenna becomes just equivalent to the radiation from these two magnetic currents. So this situation right here is known as equivalent radiating slots. And then we replace those slots with just magnetic currents in free space. And that is how you analyze the radiation from a patch antenna. But let's go back and look at this situation. Now you can see that if you increase the width of the antenna, you're then increasing the length of these slots. And if you increase the height of the antenna above the ground plane, you're increasing the width of the slots, both of which have the effect of increasing the area over which that magnetic current exists, and it gives you more radiation resistance. As you know, having more radiation resistance tends to increase the efficiency and the bandwidth of your antenna. Patch antennas in general don't have great efficiency or great bandwidth, but they're really, really compatible with printed circuit processes, and they're very flat, and they're pretty nice to deal with. And they're really easy to match and to design. So I encourage you to try out a tutorial where you build a patch antenna in FECO and mess around with it, where you get to try some of these things. Try a few different feeding methods. You can feed a patch antenna by running a microstrip line some distance into it like this. I'm making this inset distance the right location to get the input impedance you want. You can feed it from below using a coax probe feed like this through the ground plane. You can feed it parasitically by having the patch be stacked on top of your microstrip line, which just continues underneath the patch for some distance, or a variety of other things. Let's talk a little bit more about how patch antennas work from an impedance point of view. Patch antennas are often modeled by a transmission line, where you look at it and you say, okay, well, this patch is a transmission line. It's about this long. It has these slots at the end, both of which have some sort of equivalent radiation resistance. I'm going to name it RS for R slot. And the whole length of this thing is about lambda G over 2. So this is what we call a transmission line resonator. And transmission line resonators have some interesting properties, including that no matter what location you choose to put your feed point in, feed point at, the input impedance looking to the left and the input impedance looking to the right have a specific relationship when at resonance. So when you are at the resonant frequency, the impedance of the left hand, the input impedance of the left-hand side is equal to the complex conjugate of the input impedance of the right-hand side. So no matter where you put your feed point, the input impedance of this thing is going to be purely real, and then you can tune the magnitude of your input impedance by sliding that feed point around. And this is basically the transmission line model of the patch antenna. The characteristic impedance of this line is controlled by the width and the height, and this is the length, like that. Now, I told you that there was going to be some stuff about fringing fields and how those modify the length. This length is not actually the physical length, it's that length plus 2 delta L, where delta L is a length correction due to fringing. Because those equivalent magnetic currents are not right at the edge of the antenna. They're sort of in this region where the fringing fields are. So this distance is basically delta L. Same thing on the other side. I'm drawing these little electric field vectors in here. And this distance is delta L.